more power and efficiency. Let's take a look at some more applications of power and efficiency. First one, why don't we look at some of the different types of circuits? So let's get going. Let's look at a combination circuit first. This is a combo circuit. It's classically displayed with the different loads and the different resistors here, and the resistors represent the conductor resistance. And this load would then be physically closer to the source, which happens to be 120 volts, than this one, load 2. Load 2 is much further away from the source. So how are we going to solve this thing? I want to look at the amount of line loss. I want to work out the voltage across each one of the loads. And I also want to work out how many watts of power are being consumed by everything, and then maybe what the efficiency is. So let's do everything. And the first item I would then need in order to solve this would be the amount of current that each one of these loads is actually drawing. So let's look at load 2. Load 2 would, let's, I don't know, I'm going to pick a number. Let's say 17 amps. I like that, 17 amps. And this one over here, load 1, let's say that's a 15 or a 12. Let's make it a 20 amp load. All right, so we got a 20 amp load and a 17 amp load, known as load 1 and load 2. Step 1, very first step in solving this thing, we're going to apply a polarity to the source. It doesn't really matter which side you choose for it, but it just allows us to make sure that when we're aligning all of our currents, they make sense according to Kirchhoff's current law. So I'm going to do this. Current would then be leaving the negative side of the source, going through everything and coming back on the positive side. So first thing I'm going to do, I'm going to put on here all the different current values. So I'm going to use my 20 amps, and I'm going to put it here and here. And then I've got my 17 amps, so I'm going to put it here and here. And I know it seems a bit redundant, but man, there's a method to the madness, because then at these junction points, you can then start determining how much current must be entering or exiting them. 20 and 17, they're both leaving that junction. Kirchhoff's current law says they must add together to make the total amount going in. So that would be 37 amps going this way. And then down at the bottom, of course, we have the same thing, or else physics wouldn't matter and this entire discussion would be abstract. We need to be able to account for every single amp wherever it goes. Even if there's a ground fault, I should be able to track the amps through ground and wherever they happen to pop back up on the system. So now we've got current value everywhere within the circuit. Next step, I want to work out the voltages, because with the voltages, I can then work out the power values for absolutely everything. So let's work out the voltage for each of the loads. I'm going to use red for this. Load 1, 20 amps. Well, I need to know what the voltage is on each one of my conductors so that I can treat this like a closed loop and solve for the voltage of my load 1, 20 amp load. So first step, let's work out the voltage across each one of these individual conductors, which is pretty simple math with Ohm's law, because I've got 0.1 ohms and then my amperage value. So I multiply them together, I should get my voltage. Since it's only 0.1 ohms, look at this, I can do it in my head, 3.7 volts, 1.7 volts. Watch, I can do it again, 1.7 volts. And finally, 3.7 volts. All right, so now that we've done that, I can use this closed loop to apply Kirchhoff's voltage law and work out the voltage across load number 1. So load number 1, I'm going to take my positive 120 volts, my source voltage, and I'm then going to subtract these 2 line drops from it. So this one, I'm going to use my calculator because I'm not that good. I'm going to take my 120 minus 3.7 minus 3.7, and that gives me 112.6 volts. So I'm going to write that down over here. Load 1 equals 112.6 volts. Well, what about load 2 then? Well, load 2, we can do the same thing, and you have a choice. You can either go around the exterior of the circuit, the perimeter, or we can do another small loop in here, because that is, again, a closed loop. And so now what we're going to do is use the voltage for my 20 amp load and subtract the next 2 line drops. So that will be 112.6 minus 1.7 minus 1.7, giving me 109.2. All right, so now I got 109.2 volts and 112.6 volts. What do we have for power? Because power is what we wanted to calculate for this, the caption of the initial video. So power, how much line loss do I have on all these conductors? And then how much power is being consumed by the loads? So let's calculate the power of each load first. So load one, I've got 20 amps and 112.6 volts. If I multiply those two values together, what we should get is the power consumed by that first load. So 112.6 times 20 gives me 2252 watts. Down here, load 2, if I take the current value and multiply it by the voltage, that's one of my power formulas, 17 times 109.2 gives me 1856.4 watts. Now, even before we continue on, something's caught my eye and I just want to draw your attention to it. Notice the voltages here. The furthest load away has the lowest voltage, and it's quite a substantial voltage drop or line drop that we see there. The further you get from the source, the voltage that is applied to the actual load gets smaller and smaller and smaller because of the line drop on all the conductors. Let's go further to the second load. All right, so this would be my load consumption power for load 1 and load 2. What about the total line loss? So total line loss, well, that would be all of the power that is lost on my conductors. So my conductors here, all 4 of them, will have a certain amount of power that is lost in the form of heat. So that means that if I were to calculate this, I have a choice. I can either do E times I, or I can do I squared times R, or we can even do E squared over R. It's totally up to you. It doesn't matter. They'll all render the same answer. I'm going to do volts and amps. So 37 times 3.7. That gives me 136.9 watts. So that would be for the first conductor. The second conductor is 1.7 volts. So I'm going to take 1.7 times 17 amps. Gives me 28.9 watts. Now, there's 4 conductors, 1, 2, 3, 4, which means that I should be able to add all of these up yet again. And so what we get, so 28.9 plus 28.9 plus 136.9 plus 136.9, I get 331.6 watts. That's the total amount of power that is lost on my conductors due to heat. Now, what about the total percent efficiency? Well, the circuit percent efficiency would be calculated like this. We'd have percent EFF is equal to P out, so power output divided by power input. And we know that power input, or rather power output, is actually made up of what the input power minus the losses. So if we want to do this calculation, what's the total output power? Well, the output power is the power used by the loads. So 2252 plus 1856.4. The power output is 4108.4 watts. Divided by, what's the power input? Well, 37 amps times 120 volts should give us the total power input. So P in E times I. So 120 times 37. I get 4440 watts. Now, of course, there is also the added complexity of times 100, but often I leave that out because it's kind of assumed if I convert it to a percentage, then I'm going to multiply it by 100. So now I take 4108.4 divided by 4440 equals, and then times by 100, I get 92.53%. All right, so what do we have here? We have all the line loss accounted for. The line loss is here, 331.6. I worked out the power that was consumed by each one of my loads. I worked out the voltage across each one of my loads. And then finally, I worked out the percent efficiency of the whole circuit. And that's how we do a combination circuit. Quite a few rules in there in order for us to establish what is happening with all those different values. All right, what else can we do then with power and efficiency? Well, we can do power ratings. And the rating is important that you realize that a rating is only true at the rated voltage. So that's fairly important, right? Like, it's got to be the rated voltage. It's like saying my car is capable of putting out 500 horsepower on premium. What would happen if you put regular unleaded in that car? Would it still put out 500 horsepower? And the answer is no. If you're a real car buff, I mean, you'd have detonation in the cylinders, or it maybe even just fail to ignite because the compression ratio would be off for the lower octane. But that aside, what's important is that no, you wouldn't get the rated horsepower if you didn't put the rated octane in. And it's the same thing here with the power rating for electrical. If you don't put the rated voltage into this thing, it's not going to be able to put out the rated watts. And so as an example of this, if we took a baseboard heater and it was, I don't know, let's say it's rated 500 watts at 208 volts. 500 watts at 208 volts, that's a pretty common rating that we would get. At this particular rating, let's say 208 volts, and there's my heater. It's just a big chunk of resistance, and it's 500 watts is what it's consuming. I should be able to work out how many amps would then be flowing in the circuit, right? So we can take our power formulas. P is equal to E times I, which would then mean I is equal to P over E. And we could then calculate what the current value was by taking 500 and dividing it by 208. And I get 2.4 amps. Now, if you were to take that exact same baseboard heater, and let's say someone screwed up when they wired it, and instead of connecting it to 208, which actually would have required a two-pole breaker, right? Because you're going between two lines of a three-phase system. More on that in third level. But accidentally, they hooked it up to a single-pole breaker only, and then the other side to the neutral bar. That would only give them 120 volts. What if you hooked up the same heater to that 120 volt? Has the rating of the heater changed? No, it hasn't. It's still a 500 watt heater at 208. But how do you work out the current? And more importantly, how much heat it's going to put out? Well, the current value is going to change. What about the heat output? Yeah, that's going to change too. I think we can all assume that the heat output's going to go down, right? It has to go down. You're putting in less voltage, so the watts has to go down. It doesn't change the rating, but it does change what happens in reality. So at 120 volts, how do we solve this question? I mean, what do we do? It's so frustrating. Well, actually, it's pretty simple. What we have to do is take this information here and calculate what the resistance is of that particular object. The resistance is one variable that will not change. No matter what I put in, what voltage I put that baseboard heater across, the resistance will remain constant. So there's a couple of different ways that we can accomplish this. Right now, what we have is a voltage across my heater of 208, right? Because it's the only thing in the circuit. I got 500 watts and 2.4 amps. So you really have a choice as to what equation you'd want to use. I'm just going to use Ohm's law because Ohm's law is simple. R is equal to E over I, which means that 208 divided by 2.4 should give me the resistance. And 208 divided by 2.4 is 86.6 ohms. 86.6 ohms. All right, so we take that over here, 86.6 ohms. That's the one thing that will not change. 86.6 ohms, which means now that I have the new voltage in the ohms, I can work out the current and the power. So 120 divided by 86.6 gives me 1.38 amps. And from here, we can then work out the power. P is equal to, well, E times I, and also I squared R and all the rest of them. So I'm just going to keep it consistent and say E times I, well, it's 120 volts across this particular heater now. 86.6 ohms, 120 times 1.38 gives me 165.6. So how much heat is this thing putting out? Well, it's putting out very little, right? We could say it's putting out a wee bit of heat. What about the 500 watt at its rated voltage? A ton of heat, right? It's putting out its rated 500 watts worth of heat. When I only put 120 volts across it, it puts out a wee amount of heat. And so this can be a common problem when people do panel changes for electric water heaters in residential installations, and they forget to connect the water heater to the rated 240 volts and instead accidentally hook it up to 120, and you don't get half the amount of power. You get a substantially lower amount of power, right? It really, what you do is you divide that 500 watts by 3. It is 1/3 the power of the original. So it makes a substantial difference in the length of the hot water shower you can have. All right, what else do we have then? For power and power ratings and all the rest of that, let's talk about line drop very quickly. Here's line drop. That's an example, a really, really far distance to a receptacle. And you, as an electrician, are told, you know what? We're not sure that the wire has been sized appropriately, and we are concerned about the line drop. And they say, go check. Go check and see if the wire has been sized appropriately. And all we have is a receptacle way out in the middle of nowhere. Who knows where the panel is, many, many, many meters away. And they say, go check. Check. Is the line drop going to cause problems? What's the voltage? Like, what are we doing here? So how do you check? Well, obviously you're going to go and take your meter, right? There's your meter with your 2 leads. But what are you going to do? So let me illuminate you a little bit. If you were to simply take your voltmeter right now as it stands and measure the voltage across the receptacle, let's assume it's a 120 volt panel. So 120 volt receptacle. When you take your voltmeter out there and you hook it up to the receptacle, no matter what distance it happens to be and what size of wire, what's your voltmeter going to read? It's going to read the source voltage. And so this would be not the way to check the line drop. How do you check line drop on a circuit? You would have to apply a load. You would have to connect to the receptacle a load. I always like bringing a toaster because toaster is something that draws a ton of heat. And it's pretty simple to take around, never gets damaged. You would have to put a toaster or some sort of load onto the receptacle, thereby drawing current through the conductors. And when you do that, the voltage at the receptacle would change, and that would change because of the line drop. And because of that, you would get the actual voltage with the line drop, right? You would have to have a load on there. And so maybe what you would see is it drops to 110 volts. If it's a computer that is intended to be plugged into something like this, at 110 volts, that computer is probably not going to operate. It's going to shut off automatically. And so at that point, you can start evaluating the size of the conductor and see, is this actually sized appropriately, or do we need to pull larger conductors in there? So just food for thought, right? The realities of line drop and how you would go about checking them. What else do we have? Well, the last item I want to discuss is energy cost. There's your BC Hydro bill. We know in BC we have 2 separate rates that you will pay based on how much you consume. We are a little bit different in BC. like every province is. In BC, we have two-step program. So at step one, you're billed a certain amount of money, and then once you go beyond that consumption, you're billed at a different value or rate. In Alberta, it's a set rate, one rate, and it doesn't matter how much you use. You get charged that one value for any amount of energy you use. In Ontario, they charge you based on the time that you use the energy. And so that introduces some interesting situations into the electrical market regarding what type of technology we can use to help consumers reduce their overall bill. Regardless of which type of billing is used, all of us in every province are billed by the kilowatt hour. And that's because we're not billed for the watts of power, we are billed for the kilowatt hours of energy. So in order to evaluate how much you are going to be billed and how much it's going to cost you, you need to take the load and convert it into watts. Then you convert the watts into kilowatts. And then what we have to do is take the kilowatts and multiply it by the total hours that it is in operation, and that gives us the kilowatt hours. So my favorite thing, a toaster. There's my toaster. Let's say my toaster is plugged in and I eat a lot of toast. So it is a, let's say it's like a big Costco size toaster. So this thing, it's a bad boy. It's drawing like 12 amps at 120 volts. And I make toast for breakfast, lunch, and dinner. So that means that, well, on average, I eat a loaf of bread for breakfast, loaf for lunch, loaf for dinner. So I'm probably using the toaster for, let's say 3 hours a day. Three hours daily. So how much is it going to cost me if BC Hydro is charging out at 12 cents, so $0.012 per kilowatt hour, if I was to use this all year, which I do? So let's see. That's pretty simple. We take our 12 times 120 and we get the watts. So that's 1440 watts. We convert it to kilowatts, which would be 1.44. Whoops, my 4 got a little funny there. Kilowatts. We then multiply it by the total number of hours. So times 3 hours. So 1.44 times 3 hours is 4.32 kilowatt hours. Now I want to do this for a whole year. How much is it going to cost me for the year? Well, I take this number and I multiply it by 362. 365. So 4.32 kilowatts times 365 days in a year. 4.32 times 3.65. I get 15.768 kilowatt hours. How much is this going to cost me? Well, we take this value here, which is the monetary charge out for consumption, and we multiply it by this. So we got 68 kilowatt hours times 0.012. What do we get? 15.78768 times 0.012 for the whole year. Oops, that decimal's in the wrong place, isn't it? That's 1.2 cents per kilowatt hour. My apologies. Let's correct that, shall we? 0.12. There we go. And 0.12. I got to screw something up here. 0.12. There we go. So 15.768 times 0.12 gives me $1.89. I think my calculation here has been screwed up 4.32 times 365 is actually, man, I'm like so out to lunch. Good grief. So glad you shouted out there while you were watching the video and were like, Dave, what the heck are you doing? You're totally right. 1576.8 kilowatt hours. Good grief. We'll get through it together. Don't worry. So all this down here, let's just, how about we just do it over here? Okay. And that way we get a clean slate. So that would mean 1576.8 kilowatt hours times 0.12. Oh, goodness. We finally got there. Times 0.12. There we go. That makes a lot more sense. 189.21 per year. Oh, I told you we'd get through it. So, kilowatt hours. What do we need to do? We need to take the load, convert it to watts, convert it to kilowatts, multiply the kilowatts by the hours to get kilowatt hours, and then multiply the total kilowatt hours by the total cost per kilowatt hour in order for us to get the cost per year. So other than that last train wreck of an example, hopefully this was illuminating for you in sort of how we use power and what some of the different calculations are that we use.